Today's lesson is an introduction to special right triangles. There are two types of special right triangles. You have the 30, 60, 90 degree right triangle, and you have the 45 degree, 90 degree right triangle. We're going to start with the 45, 90 degree triangle. You're going to find that these patterns of solving for sides of these triangles can be very quick and efficient. Okay, look at the following pictures down below. I've already drawn figures 4 and 5. If you look at the pattern here, two of the sides are congruent each time. Well, if I have a triangle with two sides that are congruent, then we have an isosceles right triangle each time. Look for a pattern in the first three figures, then draw and label the figures 4 and 5, which I've almost already done. Well, I notice that the legs are always the same. So this must be 4 and 4, 5 and 5. And the hypotenuse always has the number that's in the leg, but a root 2 next to that. So this is 4 root 2 and 5 root 2. I've already filled out the table for us. So as the figure number increases, the length of the legs increases, and the hypotenuse is always the leg with a root 2 next to it. Okay, you might stop for a moment and think about, patterns. Looking at the pictures, you'll notice that the legs are always congruent. Hence, an isosceles right triangle, that these legs are always congruent. The hypotenuse is always the leg with a root 2 next to it. Now, what operation is happening between those two? We're multiplying. So the hypotenuse is always root 2 times longer than the legs. So, a pattern here. If we had figure n, then the legs would be n, and the hypotenuse is the leg times root 2. It's root 2 times longer than the leg. Okay, here is another way to look at the isosceles right triangle relationship. So in the square, draw on one diagonal and shade in one of the right triangles formed. Label the angle measures. Well, that's a right angle. Since it's a square, all the sides are congruent. We know by the isosceles right triangle, or the isosceles theorem, triangle theorem, that if two sides are congruent, then the base angles are congruent. And so these two angles, using math, would be 45 each. So, if one leg has a length of x, what is the length of the other leg and y? Well, this is x right here, then the other leg must be x because we originally started with a square. So the other leg is x because the original shape is a square. Now, how long is that hypotenuse? Well, we have a right triangle. We want to find the third side. So by the Pythagorean theorem, let's solve for the hypotenuse, which I've represented with h. So h squared equals x squared plus x squared. X squared plus x squared makes 2x squared. Square root both sides. And we square root the root 2. And we square root the x squared. And when you clean this up, h equals, well, the square root of x squared is nice. That's just x. We can't square root root 2 nicely, so I'm just going to leave it here. So therefore, the hypotenuse is, in words, is the length of the leg times root 2. And that's the pattern that we saw earlier. Okay, I'm going to do some examples here to show you guys how fast it can be to solve for the sides of a right triangle that's a 45, 90 triangle. And that's what we call 45, 90 degree right triangles. Okay, I encourage you guys as I do these examples that you pause the video and try them on your own first to see if you got the idea, and then go back and check the answers. Visual might help you as you solve these. Okay, I'm very visual, and that helps me figure out if I know the leg is 8, then what would the hypotenuse be? But some of you guys can do this in your head very quickly. Okay, so let's start with an example here. So the first example was the leg is 8. Okay, well, we know that this is an isosceles right triangle. By the converse, if the two base angles are congruent, then so are the legs are congruent. Okay, at any rate, so this is 8. So this leg is 8. Well, how long is the hypotenuse? Well, based on the pattern here, when I have an isosceles right triangle, the hypotenuse is always root 2 times longer than the legs. Okay, so the hypotenuse is 8 root 2. Okay, second example according to the worksheet. The hypotenuse is 17 root 2. Well, I know that the hypotenuse is the leg times root 2, so the legs must be 17 each. Of course, I should be labeling units as I go along here. Okay, the next one, the leg is 40. Well, we know the legs are congruent, so this is 40. The hypotenuse is the length of the leg times root 2, so therefore this must be 40 root 2. Fourth example, according to the worksheet, we have 10 root 2. So 10 root 2, I know the hypotenuse is leg times root 2, so the legs must both be 10. Okay, this example, a little weird. The leg is actually a radical. Well, at least I know that the legs are congruent, so 10, root 10, root 10. Okay, but how long is the hypotenuse? Well, I know from my previous exploration the hypotenuse is the leg times root 2. So therefore, I'm going to let's see here. Well, I know the leg is root 10. Okay, and times that by root 2, so I get the square root of 20. And using the skills that we learned last semester, the square root of 20 is 2 root 5. Okay, so we get 2 root 5 is the hypotenuse. Now that might seem kind of weird. You're like, how is it square root of 10, yet I have a smaller square root? Remember, this was square root of 20. Which one's a bigger number? Well, square root of 20 is going to be bigger than the square root of 10. Okay, and you can also approximate your answer if that helps you visualize it more. So we have the square root of 10, okay, which is approximately 3.16, and the square root of 20, which is 4.47. So it seems that these two answers are reasonable. The legs are much shorter than the hypotenuse. Okay, the sixth example, 16. Okay, so that's a whole number. Dang it. I'm used to having a root 2 next to the hypotenuse, so how do we solve that? Well, I know that the leg times root 2 will equal the length of the hypotenuse. So I'm going to solve for the leg. That's my unknown. So the leg times root 2 is equal to 16. Well, leg times root 2 is 16. To solve for the leg, I'm going to divide both sides by root 2. So the leg is 16 root 2. Now that's not a simplified answer, and this is why you had an earlier lesson on how to rationalize the denominator. You saw earlier, to get rid of the radical down below, I multiply the top and bottom by that radical, and then multiply across. So the leg is equal to 16 root 2 over, now the square root of 2 times the square root of 2 is the square root of 4, and the square root of 4 is 2. Okay, we can simplify the numbers outside the radical. So the leg is 8 root 2. So we got 8 root 2 times 8 root 2. And if that seems weird, how are these two numbers less than 16? Type in your calculator the square root of, or excuse me, 8 times the square root of 2. And that answer is 11.31. So it seems reasonable that my legs are shorter than the 16. Last example, square root of 6. Okay, I do know the legs are congruent. It's a nice isosceles right triangle. Square root of 6. Well, how do I figure out how long these are? Well, once again, I know that the legs times root 2 equals the hypotenuse. So the leg times root 2 is the square root of 6. I could divide both sides by the square root of 2. So the leg is equal to the square root of 6 times the square root of 2. Now you have options here. I can multiply the top and bottom by the square root of 2 and simplify. Or I do know from last semester that when I divide radicals, in other words, if I have the square root of a over the square root of b, I can rewrite that as the square root of a over b. And I'm going to use that idea here, clean that up. So the legs are equal to the square root of 6 over 2. So the leg is equal to the square root of 3. So each leg is the square root of 3. And hopefully that makes sense. Square rooting 3 is definitely going to result in a smaller number than the square root of 6.